Today we have Dr. Dallas Sherman talking about her work on marine EM. So Dallas is a postdoc in the Marine Ocean EM lab here at UTIG with Erica Tyus. And so Dallas got a PhD at Scripps Institute of Oceanography, working with Steve Constable, and worked on a number of different projects, including analysis of noise in marine magnetotellurics, and then a big project offshore Uruguay, as well as looking at methane hydrates offshore Japan, and permafrost work, which she's going to talk about today. And then after getting her PhD, she went to work for a geophysical consulting company called Frontier Geosciences, which is in Vancouver, and then started here at UTIG. So yeah, I'm very excited to hear about everything you're going to talk about. So yes, please take it away.
Excellent. Thank you, Edward. So hi, everyone. I know I met a few of you when I was back down in Austin in February when I first started. Wish I could be down there in person, but I got kind of caught up with some things up in Canada. So been out of academia for a few years. So what you're going to see today is me kind of dusting off my defense talk and going back through what I did the last few years in graduate school. Since all the data I've worked on since is proprietary and I can't talk about it. Yeah, so my dissertation was focused on using a novel surface-towed controlled source electromagnetic system to map the extent of subsea permafrost on the North Shore of Alaska. So I'll start by telling you a little bit about permafrost and why it's important. I'll introduce you to the basics of electromagnetic methods, and then show you the results from the fieldwork in the Alaskan Arctic. The picture on the title slide here is a picture from the fieldwork. That's the boat we were using. You can see our little instrument stashed in the corner, and that's one of those nice like midnight sunsets in the Arctic summer. Okay, so permafrost is defined as ground that's been below 0 degrees Celsius for over 2 years and underlies about 20% of land in the northern hemisphere. So it forms when it's consistently exposed to sub-freezing temperatures, and that cold basically conducts down and makes the ground below freezing year-round. So that's the dark blue on the image on the slide. And then since the last glacial maximum, sea level has risen between 100 and 120 meters, which has submerged the low-lying coastal permafrost. So that's where we get the subsea permafrost. It's relic permafrost that was formed on land and just hasn't fully degraded yet. And that is shown in the light blue on this map. And our survey location, you can see, is the north coast of Alaska, where we have a fairly slim region of offshore permafrost. The bulk of it is offshore Siberia, but it does play an important role in the carbon cycle. So knowing how much is out there will give us an idea of how much carbon it could potentially release as it melts. So even though the permafrost is defined by temperature, interesting things only really start happening once the fluid in the pore spaces is replaced by ice. And that's also when geophysical methods become sensitive to the permafrost. So that's ice bearing and ice bonded permafrost. Ice bearing just means some ice has started to form in the pore spaces. Ice bonded permafrost means there's quite a bit of ice in the pore spaces, and the ice and grains have kind of cemented together. I'll use the acronym IBPF to refer to a combination of both of those, and generally refer to that as ice-rich permafrost. Yeah, and that is what the geophysical methods are sensitive to is the ice in the pore fluids, not the temperature. So permafrost is a large organic carbon reservoir. This is a schematic I pulled from a paper that shows you what's going on land before it's submerged, but the idea is similar. So it takes thousands of years to form permafrost hundreds of meters thick, about 5,000 years to reach a depth of 300 meters, and over 20,000 years to reach depths of over 600 meters, which is what we see onshore Alaska. So this makes the permafrost a huge reservoir of ancient carbon. As it thaws, microbial activity will resume, consume the organic carbon, and release it to the atmosphere as CO2 or methane gas, both of which are potent greenhouse gases, and release of them would have significant impacts on climate and our future climate predictions. So the difference between the schematic that's shown here and what's happening offshore is that the active layer, which on land is the top few centimeters to tens of centimeters, sometimes up to a meter or so, that thaws during the summer and freezes again during the winter. That isn't an active layer once it's submerged. That is just a thawed layer that will continue to deepen the longer the permafrost is submerged. So the offshore permafrost is in a state of constant degradation. There's a second source of potential carbon, and that is the methane hydrate that can be associated with permafrost. Permafrost extends the gas height stability zone to shallow water and on land. So gas hydrate is an ice-like structure where water molecules hydrogen bond to one another in a lattice structure, and that cages methane molecules. It's only stable at high pressures and low temperatures. And the gases that are trapped in these kind of crystal structures are typically methane from biological sources or a gas leaking from an underlying hydrocarbon reservoir. But they're typically methane. They can contain higher order hydrocarbons such as ethane and propane. This is a common hazard for offshore drilling because, again, it'll form from gas leaking off the hydrocarbon reservoirs. It'll be stable at the low temperatures and high pressures of the seafloor under like a few hundred to a kilometer, 1,500 meters of seawater. So that's labeled gas hydrate stability zone near the kind of right-hand side of this schematic. My mouse won't show, I think because I'm in full screen mode, so I can't point to things, sorry. Yeah, so typically we're looking at the deeper shelf for where the gas hydrate is stable, which is also where offshore oil reservoirs exist. And so if you're drilling and you heat up or depressurize that gas hydrate quickly, the result is an explosion from the rapid expansion of the ice from these like caged structures to a gas. We really only see gas hydrate in shallow water and possibly onshore when it's associated with permafrost, because permafrost maintains those cold temperatures. It allows gas hydrate to exist at lower pressures. And so as the permafrost degrades, it's going to potentially release the associated gas hydrate. And so I've highlighted here the target region we're interested in. That's this shallow shelf, which is less than 100 meters water depth. Just in that region, that sea level has risen and submerged the permafrost. So there are a few different forces that impact subsea permafrost degradation. There are two conductive thermal forces. One is heat from the ocean, compared to the frigid Arctic air temperatures, the water is quite warm, still, you know, freezing, but compared to the air temperatures, it's quite warm. So you have heat coming into the permafrost from the top, and then you also have heat from the geothermal gradient, warming the permafrost from the bottom. You'll also get saline intrusion, which is just making the pore water near the surface saltier, which is going to decrease the freezing point. And it's going to help thaw the permafrost from the top just by making the pore fluids more saline. And then you also have effects from local hydrology. So freshwater influx from groundwater, which would do the opposite from the saline intrusion. It would freshen the pore fluids, which would raise their freezing temperature, and they'd be more likely to refreeze. And then the large rivers are also a heat source. And so you can end up with talics or areas that are unfrozen and otherwise continuous permafrost along these riverbeds. So there are two different ways that before this project, people had measured subsea permafrost in the past. One is just with boreholes. So there's an example of one borehole here. And then the other is seismic, specifically seismic reflection, which is from the Brothers et al. 2012 paper. So of the 5 logs from the borehole shown here, only 2 of them strongly indicate where there is ice present in the overburden. I don't even really remember what the first 3 are, but they don't show much. The last 2 are resistivity and seismic velocity. The highlighted pink areas are high saturation ice-bonded permafrost, and the orangish highlight is more an intermediate ice saturation, ice-bearing permafrost, and the white is no evidence of permafrost. I believe this was cored, so I believe those were like visual evidence. So for resistivity, we're looking at a resistivity of about 100 ohm meters for that high saturation ice-bearing permafrost, ice-rich permafrost, and then more like 10 ohm meters for the lower saturation ice-rich permafrost. So the issues with boreholes are obviously that it only gives you information at one location. It's very hard to extrapolate from that. A couple issues with seismic. To get the seismic velocity, doing a seismic refraction survey is a lot more labor intensive. The seismic reflection over water, you can get a lot of data fairly quickly, which is what we're looking at in this lower figure here. I believe in this paper, they're showing you on the left an example of just the seafloor refractor, an example of the permafrost layer refractor, the PLR, and then lastly, an example of the seafloor and a bedrock refractor. So the issue with reflections off of the permafrost layers, you'll get a very strong response at the top when the ice-bearing sediment starts, but you won't get a strong signal from the bottom. So the extent of permafrost mapped by these seismic surveys basically give you a top of permafrost. So it gives you a lateral extent. It doesn't give you any information about the thickness of the permafrost layer or how much ice that layer might contain. And so what we are trying to do what we were trying to do by using an EM, a towed EM system, is to be able to cover the same kind of ground you would cover with the seismic reflection, but add an idea of where the base of the ice-rich permafrost is and an idea of how much ice is actually present, what the kind of ice saturation might be. So there's a reason the resistivity axis was a logarithmic axis and the seismic velocity was not. And that's because, as you can see in this figure, the resistivity of Earth materials spans a huge number of orders of magnitude. So there are a ton of these kinds of figures. This one appears to be somewhat focused on exploration. So I've added the range where ice-rich permafrost is. It does overlap with fresh groundwater in the kind of 10 to 100 ohm meter range. A couple other points of note would be marine sediments. So that's sediment that has seawater in the pore fluids are typically around 1 ohm meter. And for the most part, we expect more overburden than we could sense. So we don't anticipate running into bedrock for the most part. We'll be looking at a resistor in an otherwise conductive overburden section. Okay, so that's what the EM method is going to be sensitive to. We're looking for that resistive layer against a conductive background. Going to get into some of the details about the method and the equipment we used. So the basic equation we're working with is the wave equation, which simplifies to the diffusion equation because of the low frequencies we operate at. The skin depth describes the attenuation of the electromagnetic energy. So you can see that the skin depth is dependent on both the resistivity of the subsurface and also on the period or the frequency of the signal. So higher subsurface resistivity and lower frequencies or longer periods are going to penetrate deeper, and higher frequencies are going to attenuate faster and will only be sensitive to the surface sections. Because we are dealing with the diffusion equation, that does mean the resolution depends on depth. So if you have 5 meter anomaly right near the surface, that's something we could be sensitive to. You move that same 5 meter anomaly down 100 meters, it's going to be completely invisible to the method. So this is a schematic of the system we were using. Looking up in the A figure at the top, a little schematic of the boat. We have a transmitter that's on the boat, and then we have a 50-meter antenna that we put in the water. And then we have 4 receivers that are measuring the inline electric field, and they're spaced at 250, 500 meters, 750, and 1,000 meters offset. And so in addition to frequency, determining what our depth sensitivity is, source receiver offset is the other big thing that affects the depths we're sensitive to. So again, because this is the diffusion equation, by the time that electric field reaches the first receiver, it's only gone through the shallow portions of the subsurface, whereas by the time it reaches the last receiver, it's been able to traverse much deeper. So the longer source receiver offset, the deeper we'll be able to sense. This is just a quick zoom in of the actual receiver design. Very conveniently, because we're towing at the surface, we can just put GPSs on our receivers. So we do actually know where the receivers are. which is quite fantastic because this is based on our deep tow design where all these receivers are, 2,000 meters under the water, and you kind of have to work out where they are. And that's like the hardest part. So we've made that very easy. GPS is on there. We are only measuring the inline electric field, which is the strongest component. And then we also have accelerometers, pitch roll heading sensors, so we can make all those kinds of corrections. So before we get into some data, just a quick explanation that we are measuring the electric field, which is a complex number, and we represent that as amplitude and phase. So this is just one example of a short clip of raw data at the top, and then how that would be represented in amplitude and phase. So this is just a quick sensitivity model experiment that I did to help us determine what frequencies we should use during our survey. So I took a very basic 1D layered model of 200 meters of marine sediment on top of a 200 meter thick layer of ice-rich permafrost, and then a return to marine sediment. So over on the left, we have our amplitude response. So that's the ratio of the model response with the frozen layer over without the frozen layer. And then I believe the phase is just a phase difference. So frequency on the vertical axis, so lower frequencies towards the bottom, which would be sensing deeper. Source receiver offset on the horizontal axis. So you can see the arrow of kind of increasing depth sensitivity there. We ended up using a fundamental frequency of 1 Hertz, which results in the strongest harmonics of 3, 7, and 13 Hertz, which is shown by the magenta square there. And the offsets were between 250 and 1,000 meters. The amplitude is much more reliable than phase. So we're going with those lower frequencies to capitalize on that difference. The maximum of 1 kilometer offset is just logistical. It's hard enough to tow a surface array that's a whole kilometer long, and it wouldn't have been feasible to do any longer. So a couple of field photos of us deploying a receiver in the bottom left corner there. Top left corner is just the receiver in the water with its GPS head sticking up there. And then we had one really clear day where we could actually see all 4 of these receivers, which we called porpoises, behind the boat. And then you can see the sea ice in the back there. There was kind of a cool mirage. It makes it look like there's a giant ice wall. There's not, it's just the floating sea ice. Okay, so finally getting to the specifics of the survey location. So we were in the Beaufort Sea on the north coast of Alaska, flew into Dead Horse, which is not so much a town as it is a camp for all of the North Shore oil workers. And this figure is a nice summary from the Brothers et al. 2012 paper of what the marine seismic reflection told us about the extent of permafrost. So the yellow mark there is the extent of permafrost at the last glacial maximum. So that's the 120 meter isobath. And then the red is the 20 meter isobath, which is where the seismic reflection data suggested the ice-rich permafrost stopped. So all of our data ended up being collected inside that 20 meter isobath. And so we were really interested in getting an idea of, like I said, how much ice and how thick the permafrost was in that area. So these are the line locations that we collected. We collected 2 years of data, summers of 2014 and 2015. 5 days the first year, 7 days second year. The 20-meter isobath basically falls right outside all of those little barrier islands. And unfortunately, that is also where the sea ice sat the entire time we were there, both years. So we were restricted in how far out we could collect data. So we weren't able to get a direct comparison for seaward extent of the edge of permafrost to compare to the seismic data, which is unfortunate, but it's the way it was. So I will show you 2 toes in detail. It's toe 3, which is shore parallel and crosses the Sagavanirtak River outflow. It's written on here as Sag River for short. And then I'll also show you toe 2, which is the longest shore perpendicular line we were able to collect. And then I'll also show you one borehole, Badami 2, which is near shore in the southeast corner there. So our basic workflow, we transmit our fundamental waveform, we record that inline electric field with the receiver, Fourier transform it and stack it into 1-minute intervals, display the complex numbers as amplitude and phase, and then that amplitude and phase at various frequencies and offsets are the input to the inversion program we use. So we use Carey Key's Mari 2D EM, which is an adapted for finite element inversion code, and it uses the Occam inversion method. So I'm going to skip through these next couple of slides. The important thing to know about the Occam inversion method is that it assumes you understand the noise structure of your data well and have assigned accurate uncertainties to each datum. You then set a desired misfit. So say like an RMS of 1 or whatever you think is appropriate given the uncertainties you've assigned. The Occam inversion iterates until the RMS equals 1 is reached. This is the point where most deterministic inversion algorithms would stop, or they would keep trying to drive that misfit down until it stops changing an appreciable amount. What the Occam inversion does instead is once it reaches that RMS of 1, it then searches for a smoother model that fits the data to that same RMS value. So there is always a trade-off in inversions between how well the model fits your data and how smooth the model is. Left to the computer's own devices, it would give you something absolutely pathological that fit the data really, really well, but was completely geologically useless. And so the Occam inversion is operating on the principle of Occam's razor, which is that the simplest explanation is often correct. So in this case, our definition of simple is smooth. So it's looking for the smoothest model that fits your data. So just keep that in mind when we're looking at the results. The Occam inversion does a really good job of smoothing out artifacts, but it does produce a smooth model result. Okay, so this is that shore perpendicular line, toe 2. So the inline distance 0 is near shore, and then it goes for almost 8 kilometers offshore. As expected, the blue portion, which is the resistive ice-rich permafrost layer, does thin as it gets offshore. And for at least the first 6 kilometers, it appears to thin mostly from the bottom. So it looks like it's mostly melting from the bottom up as opposed to the top down. Except for that last kind of 2 kilometers, it looks like most of the degradation has come from the surface. Yeah, and so these resistivities are consistent with what we saw in the borehole I showed you earlier. The dark blue is that 100 ohm meter and higher, which would indicate high saturation ice-bearing permafrost. And the darker red is more indicative of unthawed sediment. Just for reference, these are the amplitude model to data fits. This inversion was isotropic, so we're assuming that the resistivity is the same in all directions. And this was an amplitude only inversion. We ran into some issues with our phase data from the first year, so I did not have good phase data for this line. Yeah, the next inversion I'm going to show you is TOE3, which intersects this line, as I've noted here. And TOE3 did have good phase data. And once I added the phase data, the isotropic inversion wasn't able to fit both the amplitude and the phase. And I needed to allow for transverse anisotropy to get that phase, model phase to agree with the data phase. So the electrical anisotropy is basically the idea that the measured resistivity in the vertical direction will be different from the measured resistivity in the horizontal direction. So this would make sense in the permafrost context because as ice starts to form in the pore fluids, the ice is obviously resistive, but it does exclude ions from the ice formation. And so you could end up with kind of ice layers and then high saturation of ion pore fluids, which would be kind of resistive and conductive layers together. So looking vertically, because we're horizontally layered, that's the equivalent of kind of connecting resistors in series. So you're going to end up with a higher resistance because the current has to flow through that highly resistive layer. The horizontal resistivity is going to be more sensitive to the conductive layers because it's like connecting those resistors in parallel. And so current can preferentially flow through the path of least resistance. And so that is what we see on this TOE3. Again, this TOE3 intersects with the TOE2 and it goes across this river. So we have horizontal resistivity up top, which is pretty universally values consistent with thawed sediment, as we would expect. The vertical resistivity is where we're sensitive to the ice-rich layers. And again, we get a lot in that 100 ohm meter range, which indicates high saturation of ice. And then the last thing is the anisotropy ratio, which is just the ratio between the vertical and the horizontal. If we compare the vertical resistivity to the isotropic TOE2 inversion, the vertical resistivity never quite returns to the like less than 10 ohm meter thawed sediment value. And I think that has a lot more to do with the regularization of the inversion than it does with what's actually happening. And so I found that the anisotropy ratio gives us a better idea of where the base of permafrost would actually be. So that's what I use in a minute to kind of create plan maps of the depth to permafrost. The other thing to note here is this does cross the river outflow, and it crosses the river outflow kind of between 15 and 26, 27 kilometers inline distance. So that's where the depth to the top of the permafrost is much less. There's permafrost nearly on the ground surface, and that's likely due to some fresh groundwater intrusion coming into this thermal regime where the ground is probably a couple degrees below freezing, which would mean thawed marine sediment, but means frozen freshwater sediment. Okay, so we're just going to take a look at possible anisotropy in the borehole logs. So this is that Badami borehole. The black is the raw borehole log. And then in column A, I have calculated the average vertical and horizontal resistivity. The vertical being that adding up the layers in series, horizontal, adding them up in parallel. And then in column B, calculating the anisotropy ratio. And then column C is the corresponding ice saturation, which I'll explain on the next slide. So the anisotropy ratio isn't continuously high through the entire ice bonded permafrost section, but it is only elevated during that section, and the transition areas are where it's the highest. So defining the base of the ice-rich permafrost with that anisotropy ratio, I think is a good way to go. So the ice saturation calculation is just a reformation of Archie's law, which is a not great empirical formula that is kind of the best we have to correlate resistivity measurements to porosity and things like that. So I pulled a lot of these constants from various publications and used this formula to calculate the ice saturation of these two toes. And so as expected, the kind of dark blue high saturation ice bearing permafrost over 100 ohm meters is going to apply more than 80% if your pore fluid is frozen. And in the top isotropic inversion, the 0% is pretty close to that 10 ohm meter contour, which is what I use in the isotropic inversion to define thawed versus ice-rich permafrost. Okay, so with that in mind, I've only showed you 2 inversions. We collected over 20 lines. So I inverted all 20 of those. And then I used the 10 ohm meter contour to define the top of permafrost. And then either the 10 ohm meter contour or the anisotropy ratio, depending on the year, to define the base of permafrost. And then I combined that information from all 20 lines to create these plan maps of permafrost extent. So this one is the depth to the top. Consistent with what we saw on that toe 3 I showed you, the shallowest permafrost is right off that Sagamore-Nurtaq River outflow. The circles are the borehole values, and the biggest discrepancies there are the ones near Jones and Long Island. And that's because those were drilled on the barrier islands and not actually in the subsea environment. So they're on the islands, they are still exposed to the frigid Arctic air. So I think that's why those are so different from what our data saw. So this is basically the same information we would have gotten from the seismic survey. What we are adding to the discussion is the depth to the base of the permafrost. And so we're seeing the deepest permafrost over 500 meters, getting close to 600 meters deep in the eastern area, down by that Badami borehole that I showed you. And even though offshore the Sagamore-Nurtaq River, the permafrost is shallower, but it's not necessarily as deep. Gets deeper again, moving further west. And I'll talk more about what's happening offshore the Colville River in the next couple maps here. So then obviously it's easy to get the thickness from those two. And there's, again, some discrepancies between this and borehole measurements. Again, mostly in those ones that were actually drilled on the barrier islands. And then the other difficulty with getting the top and base from the boreholes and comparing those to our data is it's not taking into account yet the resistivity or the amount of ice present. And so in this last map, sorry, I went the wrong way. This is peak resistivity. So this would be like the maximum ice saturation found. And so on the far left side of this figure, over by the Colville River, there were only 3 lines collected here, and now there's a 4th. And the reason for that is this last line, you can see it's very orangey. So it has very low resistivities, indicating this entire section was completely thawed. And even that borehole has relatively low resistivities. So my thought was kind of the Colville River is a much bigger river than the Sagamore River. And it's quite likely it's kind of paleo bed is out there. And that is a talc feature. So there's this area of unfrozen and otherwise continuous permafrost. And then the Sagamore is a smaller river, and we're seeing the freshening of pore fluids offshore it. Okay. I think that's about my time. And this is pretty much my last slide. So the idea is that the original thinking here was that there was probably some amount of permafrost, you know, from shore all the way out to the 100-meter isobath. You know, maybe it got discontinuous out there, but it was kind of thought most of the shelf had some amount of permafrost. And so I couldn't find a paper with a nice like shore perpendicular figure like this. So I made a stupid one. This is a very basic conduction only estimation of permafrost formation, which is the blue. So at the last glacial maximum, you would expect the blue amount of permafrost to be in existence. And then assuming that last sea level low stand lasted about 5,000 years, and that sea level rose at a steady rate over 20,000 years, and that only conduction affected permafrost degradation. The red is what you would expect today. The seismically inferred edge of permafrost was that 20-meter isobath, which is significantly closer to shore. And then the EM data, you know, shows a base of 300-400 meters in that 10-meter water depth area. And so far the observations suggest that we were dramatically overestimating how much there might be on the shelf. But then one of you before the talk was saying your models showed that there would be none in the Beaufort. So I'm interested to hear about that. Okay, so quickly, conclusions. We did successfully use this new surface-towed controlled source electromagnetic system to map ice-rich permafrost. We did find that the permafrost was anisotropic, which helped distinguish it from freshwater saturated sediments. So I think it's going to be a useful tool for mapping permafrost in other locations. And this is something that I'm hoping to maybe continue or maybe even collect some data on land and continue using EM to understand the dynamics of permafrost degradation. Biggest acknowledgement, this work was funded by the Department of Energy. And then Oh, that's one inside joke left, sorry. And then I have all of my references. Okay, I'm ready for questions. Hang on, my speaker turned off or died or something.
Can you hear us now?
Yeah, I can hear you now. My speaker turned itself off, sorry.
Yeah, great talk. Does anyone have any questions in the room or also online?
Tell me about, I didn't get his name. Were you saying something about?
Oh, yeah, okay, so I did some research in the Beaufort, but that was mostly on wave-driven transport of sediments. So we were only concerned with the top few layers of the seabed. And so we were really concerned that there might be permafrost outcrops on the sea surface that might be really resistant to erosion. And,
Okay.
and so it looked like your models got to about 5 meters from the sea surface that where we might see permafrost. Is that right?
Yeah, I think so. And that was actually something I was thinking about as well, in terms of, I don't know much about like how the barrier islands form, but they do move. And I was wondering if there was any relation. So were you looking more at like coastal erosion or?
Sorry?
I think I'm still not understanding the scale or like exactly where you were looking at how this might relate.
Oh, right. So we're modeling wave-driven erosion within the few meters of the seabed. And so if there's permafrost, exposed on the surface of the seabed, that could be really erosion resistant and impact our model results. And so we assumed our seabed was completely unfrozen.
Okay. Largely probably fair.
Excellent.
Yeah, I think it was really only in the one it's very annoying that I don't have my mouse. I think the only place that we saw higher resistivities at surface was really in the off flow of the Saguenay River. But other than that, yeah, surface totally unfrozen for you.
That's great news.
I have a question. Thank you for your talk, Dallas. This is Benjamin. Nice to see you. There were really big, can you go to the next slide, the depth to the bottom? You mentioned that one of the things that can be like driving the permafrost to melt from below is just a geothermal heat flux. And so I'm wondering if, but you see these really big variations in the depth at the bottom. So do you think those are all driven by natural variations in the geothermal heat flux, or are there other things that are changing the rate at which it's thawing from the bottom up?
That is a very good question. Interesting. So,
thank you.
Okay. I hadn't actually thought that through before.
That's totally fine.
But I think the only thing affecting it from the bottom would be the geothermal gradient. And so I think the big variations in the depth to the base will probably be a result of the local hydrology and just maybe the original formation being uneven as a result. So it is quite possible that the shallowest bases do tend to be also offshore these rivers, which.
That's interesting because the river's like protecting it from melting from the top, kind of.
Yeah. So they're kind of the rivers are both a heat source, especially during the formation period. There won't typically be permafrost formed in the bed. But yeah, now that it's submerged in the shallow part, yeah, you're getting the freshening of the pore fluids that kind of refreezes it at surface. So that would be my best guess for those variations. Because yeah, I can't think of another heat source that would come from the bottom.
Thank you.
What's the bedrock geology here?
It's a really good question. And I don't actually know. I just think that it was I think
That's what I was asking.
Kilometers down, I would guess.
yeah. I think on the one of them at the
I was just trying to get an idea of like what heat flow would be in this part of the world.
yeah, I don't actually know. I think the seismic reflection maybe saw like 4 bedrock refractors ever. So I was just operating under the assumption that for my purposes, bedrock didn't exist.
I have another question.
Yes.
Do you know what the like paleo environment that this was forming in was like? And like, for example, were these rivers likely in the same place? I mean, one of the interesting things about Alaska is that is one of the few regions of the Arctic to not really have big ice sheets during these cold periods. And what the explanation that I've heard for that is that it was just pretty arid. And I wonder if that also would like drive there to be variations in the thickness of the permafrost or sort of limit permafrost development, or do you like not actually need that much water to make permafrost, or yeah?
Yeah. So again, there's kind of the permafrost versus there actually being ice present, right? So yeah, you do need some amount of water in the ground. So it can't be too dry to form the ice-rich permafrost. I don't know that much about the environment in Alaska where the permafrost formed, other than that it was unglaciated, which means it was exposed to all of that very, very cold Arctic air, which is why the permafrost formed so thick. The ice can actually tend to be a bit of an insulator. So you get obviously deeper permafrost in areas that were extensively not glaciated.
Interesting. I didn't realize that.
Yeah. But yeah, I don't really know any other details.
Well, thank you.
So that's the porosity was consistent across that region. I didn't see well the well logs.
I don't know that they measured porosity specifically. I think I just had to make a reasonable guess for porosity. I don't think I had very good information on that.
Do all the like oil fields in that region like affect your data if they're like similar resistivity values, or is it like pretty easy to like tease them apart?
I think they're typically deeper than we were sensitive to, but they do overlap for sure. Yeah, they do overlap. But I think for the most part, there are the big reservoirs anyway would be a bit a bit deeper, I think. The potential bigger issue actually was infrastructure out there. We towed over one pipeline or something that nobody knew was there. And it just kind of looks like a random like Gaussian spike in your tow data. And you're like, that doesn't look natural. That looks like we drove over. So that was obviously eliminated from any further interpretation. Yeah.
Do we have any more questions for Dallas? Well, if not, let's wrap it up here. Thank you very much once again. It was a really interesting talk and good to hear about everything you're doing.
Yeah. Thanks for all your questions. Hope your snacks are delicious.